On June 25, 2025, a team of astronomers published a paper in the journal Nature that quietly closed out a 3-year wait. For as long as the James Webb Space Telescope had been operating, since its very first science images were released back in the summer of 2022, it had photographed nebulae, galaxies, colliding black holes, and the atmospheres of planets we already knew existed. But it had never found a brand new planet entirely on its own, using nothing but its own eyes, catching the planet's own faint light, rather than inferring its existence indirectly. That changed with a single, faint, orange smudge of infrared light, tucked inside a ring of dust around a young star called TWA-7, roughly 111 light-years from Earth. The planet is called TWA-7b. It's the lightest planet ever directly photographed around another star, and the story of how astronomers found it, confirmed it, and what it might mean for how planets form, is genuinely one of the most remarkable real achievements in the history of exoplanet science. No exaggeration required. Let's start with why this milestone took so long to arrive, because the delay itself is part of the story. The overwhelming majority of exoplanets discovered since the 1990s, and there are now more than 6,000 confirmed, were found using indirect methods. The most common is called the transit method, where astronomers watch a distant star's light very precisely and look for tiny, repeating dips in brightness caused by a planet passing directly in front of it from our point of view. Another common technique, called the radial velocity method, looks for a slight wobble in a star's motion caused by the gravitational tug of an orbiting planet. Both methods are powerful, and together they've built almost the entire modern catalog of known worlds beyond our solar system. But neither one actually shows you the planet. You're inferring its existence from the effect it has on its star, the same way you might infer a person is standing behind a curtain because you can see the curtain move. Actually seeing a planet directly is a completely different and vastly harder problem, and the physics behind why explains a lot about what makes the TWA-7b discovery so significant. As lead researcher Anne-Marie Lagrange, an astrophysicist at the French National Center for Scientific Research, put it plainly when describing the challenge to reporters, the basic problem is that the star is bright and the planet is very faint. Stars generate their own light through nuclear fusion, blazing with energy. Planets, especially the cooler, older ones, mostly just reflect a tiny fraction of their star's light back, or in the case of a young, still cooling planet like TWA-7b, glow faintly in infrared from their own leftover formation heat. The difference in brightness between a star and a planet sitting nearby can be a factor of 1,000,000 or more, and when you're trying to observe both from many trillions of miles away, that overwhelming glare simply drowns out the planet entirely under ordinary conditions. It's the astronomical equivalent of trying to spot a lit match held next to a lighthouse from the other side of an ocean. To get around that problem, Lagrange and her team used one of Webb's most specialized tools, a coronagraph, which is essentially a precisely engineered mask built into the telescope's optics that physically blocks out the light coming from a star's exact position, allowing much fainter objects nearby to become visible. Even with the coronagraph doing its job, some scattered starlight inevitably leaks through and has to be mathematically subtracted out using advanced image processing techniques, comparing the target star against reference stars, and carefully modeling exactly how the leftover glare should behave, so it can be cleanly removed. Once all of that processing was complete, sifting out every trace of stray starlight from the raw data, a single faint point of infrared light remained, sitting inside the gap of one of the star's 3 concentric dust rings, exactly where a planet with a right mass would be expected to carve out a clearing. That gap wasn't a surprise to researchers. Astronomers had actually been curious about TWA-7 for years before this discovery, precisely because of the structure of its debris disk. As astronomer Robert Leah explained, describing the setup, from Earth's vantage point, we happen to see the star's surrounding disk of dust and debris nearly face-on, rather than from its narrow edge, which is a rare and useful viewing angle. That face-on view let earlier ground-based telescopes clearly resolve the disk into 3 separate rings, with a distinct gap carved into one of them. Gaps like this are a well-known signature in the study of young planetary systems. A planet orbiting within a disk of leftover dust and debris will gravitationally sweep up or scatter material along its path, carving a visible clearing exactly at its orbital distance from the star, roughly the same way a snowplow leaves a clean track down the middle of a road. Astronomers had suspected for years that something was likely orbiting inside that particular gap. Webb's coronagraph finally let them look directly at it and confirm what had only been inferred before. The numbers involved are worth sitting with for a moment because they're genuinely remarkable on their own terms. TWA-7b has an estimated mass roughly similar to Saturn, one of the giant planets in our own solar system. It orbits its star at a distance of about 50 times the distance between Earth and our own Sun, an enormous wide orbit by the standards of most previously confirmed planets. Its estimated temperature comes out to around 120 degrees Fahrenheit, remarkably mild for a young giant planet still glowing with the leftover heat of its own formation. And the star it orbits, called TWA7, is itself only about 4 million years old, an infant by stellar standards, still surrounded by a sprawling ring system left over from its own birth. But the detail that made this discovery so scientifically significant isn't the planet's size or its temperature. It's how little of it there actually is to see. TWA7b is estimated at only around 100 times the mass of Earth, or roughly 3/10 the mass of Jupiter, making it, according to the research team's own comparison, approximately 10 times lighter than any planet ever previously imaged directly around another star. Every single planet astronomers had managed to photograph directly before, this one was significantly heavier, and therefore significantly brighter and easier to spot. TWA7b represents an entirely new, much fainter category of world that had simply never been within reach of any telescope's direct imaging capability until Webb came along. There's a healthy dose of scientific caution built into this discovery too, and it's worth including because it's part of what makes the finding credible rather than sensational. The research team was careful to acknowledge that there remains a small quantified possibility, calculated at around 0, 34%, that the infrared source they detected could actually be an unrelated background galaxy happening to sit at almost exactly the same position in the sky, purely by chance, rather than an actual planet orbiting TWA7 itself. That's a real stated uncertainty, not something glossed over in the announcement. To rule out that possibility and strengthen their case, Lagrange and her colleagues built detailed computer models simulating what a genuine planet of roughly that mass, orbiting at roughly that distance, should look like given everything already known about the shape and structure of the surrounding dust disk. When they ran those simulations, the predicted appearance matched almost exactly what Webb's coronagraph had actually captured, giving the team enough confidence to publish. As Lagrange told Science News, that matching result was really why the team felt confident there was a genuine planet there, rather than an unrelated interloper. It's also worth noting, because it's a detail that rarely survives translation into more sensational retellings of this story, that this wasn't actually the very first time Webb had ever captured an image connected to an exoplanet. Back in September 2022, shortly after Webb began science operations, the telescope captured a direct image of a gas giant called HIP 65426b, a planet with a mass somewhere between 6 and 12 times that of Jupiter, located about 385 light-years away. That earlier image was itself a genuinely historic moment, described at the time by University of Exeter astronomer Sasha Hinckley, who led that observation as a transformative moment not just for Webb, but for astronomy generally. But HIP 65426b had already been discovered years earlier by a different telescope, an instrument on the ground called the European Southern Observatory's Very Large Telescope. Webb's 2022 image simply confirmed and rephotographed an already known world with much greater clarity, demonstrating that its instruments worked as designed. TWA7b is a different kind of milestone entirely. It's the first time Webb has ever found a completely new planet, one nobody had previously confirmed to exist, using nothing but its own direct imaging capability from the very start. So why does any of this actually matter, beyond simply adding one more entry to the growing catalog of known worlds? The significance here runs in a few different directions, and each one connects to genuinely important open questions in astronomy. The first has to do with planetary system formation more broadly. TWA7b appears to be sitting precisely within the gap in its star's debris disk, in exactly the location models had predicted. A planet of its mass should be shaping the surrounding material. If that connection holds up under further study, it would represent the first time astronomers have directly imaged a planet that can be clearly tied to actively sculpting the disk around it, offering a rare, concrete visual link between a young planet's presence and the physical structure of the debris field it's carving through. That's valuable because it lets researchers test theoretical models of planet formation against real, observed geometry, rather than relying purely on simulations and indirect inference. The second reason this matters is about instrumentation and opportunity. Co-author Mathilde Mellon, an astrophysicist at the Space Telescope Science Institute, described the broader implications succinctly, noting that Webb opens up an entirely new window in terms of both mass and orbital distance into a whole category of exoplanets that had simply never been observationally accessible before. Every planet directly imaged prior to this one had to be substantially heavier and brighter than TWA7b, just to be detectable at all, which meant an entire population of smaller, fainter, more Saturn-like, or even eventually Neptune-like and rocky worlds set completely outside what any existing telescope could actually see with its own eyes. Lagrange herself, in comments to Reuters, framed the significance in similarly broad terms, describing this expanded observational reach as important for exploring the genuine diversity of planetary systems across the galaxy. and for understanding how such systems actually form and evolve over time, insight that ultimately deepens what we understand about the origins of our own solar system as well. And the third reason, perhaps the most quietly exciting one for researchers working in this specific corner of astronomy, is what it signals about what comes next. TWA-7b was 10 times lighter than anything previously imaged directly. That's not likely to be the practical floor of what Webb, or future instruments building on its techniques, will eventually be capable of detecting. Every one of the underlying challenges that had to be solved to make this observation possible, refining coronagraph performance, improving the mathematical modeling used to subtract residual starlight, building confidence through matched computer simulations, represents a technique that can now be applied again to fainter targets around other young stars with their own debris disks and their own unconfirmed gaps hinting at hidden worlds. Researchers in the field, including Beth Biller of the University of Edinburgh, who wasn't involved in this particular study but reviewed its findings, described TWA-7b as poised to become genuinely important for opening up an entirely new realm of cool exoplanet atmospheres that astronomers can now begin to characterize in detail, atmospheres belonging to planets that, until this discovery, would have been considered simply too faint to study this way at all. It's worth placing TWA-7b within the broader history of direct exoplanet imaging, because that history helps explain exactly how big a leap this discovery represents. The very first exoplanets ever directly photographed came in 2008, when astronomers announced images of multiple giant planets orbiting a star called HR 8799, all of them many times the mass of Jupiter, bright enough to stand out clearly even with the telescope technology available at the time. That same year, a separate team announced a direct image of a planet orbiting the star Fomalhaut, though later analysis raised questions about whether that particular object was a true planet or a transient dust cloud. In the years since, ground-based observatories equipped with increasingly sophisticated instruments, including the Very Large Telescope's SPHERE instrument and the Gemini Planet Imager, added a handful more directly imaged worlds to the catalog, virtually all of them massive gas giants, several times heavier than Jupiter, orbiting relatively far from their stars, where the contrast between star and planet brightness is somewhat less extreme. Every single one of those earlier successes depended on the same basic requirement. The planet had to be bright enough, meaning massive and hot enough, to punch through the technological limitations of the instruments doing the looking. TWA-7b breaks decisively from that entire pattern, not because of some entirely new principle of physics, but because Webb's instruments, operating in space, above the distorting effects of Earth's own atmosphere, finally pushed the sensitivity threshold low enough to catch something in an entirely different weight class. The specific instrument responsible for the observation, Webb's mid-infrared instrument, known by the acronym MIRI, deserves its own moment of explanation, because the choice of instrument mattered enormously here. MIRI is uniquely suited to this kind of search because young, still cooling planets like TWA-7b radiate much of their leftover formation heat specifically in mid-infrared wavelengths, a part of the light spectrum that Earth's own atmosphere blocks heavily, making this kind of observation essentially impossible from any ground-based telescope, no matter how advanced its optics. Webb, positioned far from Earth at a gravitationally stable point called the second Lagrange point, roughly 1 million miles from our planet, operates with an unobstructed view and instruments cooled to extraordinarily low temperatures, allowing MIRI to detect the faint thermal glow of a young planet without that signal being swamped by heat radiating from Earth's own atmosphere, or from the telescope's own components. That combination, a coronagraph physically blocking the star's light, paired with an instrument built to detect exactly the faint infrared wavelengths a young planet would naturally glow in, is what finally made a planet as comparatively faint as TWA-7b detectable at all. It's also worth understanding a bit more about what these dust rings around young stars actually represent, because they're not just decorative structure, they're active fossils of planet formation still in progress. Stars like TWA-7 form from collapsing clouds of gas and dust, and in the early millions of years of their existence, they remain surrounded by a flattened spinning disk of leftover material, the same basic raw ingredients that, over time, clump together to build planets, moons, and asteroids. As planets begin to form and grow within that disk, their gravity gradually clears out neighboring material, pulling in nearby dust and small rocky bodies, or flinging them onto different orbits entirely, carving out visible gaps in what would otherwise be a smooth, continuous ring. Astronomers have used exactly this kind of gap-hunting technique for years, studying disks around other young stars to infer the likely presence of unseen planets long before any telescope could actually see them directly. TWA-7's disk had already been resolved into 3 distinct rings by earlier ground-based observations, specifically because of that unusually convenient, nearly face-on viewing angle from Earth, and the particular gap where TWA-7b was ultimately found had already been flagged years in advance as one of the more promising places to look for a hidden world. Looking ahead, This discovery also connects directly to some of the most ambitious astronomical projects currently in development. Multiple space agencies are actively planning future missions, specifically built around the goal of direct exoplanet imaging at an even more advanced level, including concepts designed to eventually image Earth-sized rocky planets around sun-like stars, something far beyond even Webb's considerable capabilities. Every technique refined during the TWA-7b observation, the coronagraph engineering, the starlight subtraction processing, the simulation-based confirmation method used to validate the detection, feeds directly into the broader body of knowledge those future missions will build on. In that sense, TWA-7b isn't just a single new entry in the exoplanet catalog. It's a working proof of concept for an entire future generation of planet hunting instruments, demonstrating in a real, peer-reviewed, published result that the basic strategy of blocking a star's light and catching a planet's faint infrared glow can be pushed meaningfully further than anyone had previously managed. Webb had already spent roughly 3 years in operation, since it began returning science images in mid-2022, steadily refining and calibrating its coronagraphic instruments across dozens of other observation programs before this particular team turned its attention specifically to TWA-7. The star itself had already been studied for years by ground-based telescopes precisely because of its unusually convenient face-on viewing angle, which had already hinted indirectly that something might be hiding in that gap in its disk long before Webb's coronagraph ever confirmed it. This wasn't a lucky, unplanned accident. It was the product of a carefully targeted observation, aimed at a specific star system chosen because prior research had already flagged it as an unusually promising candidate, executed using an instrument built and calibrated over years, specifically to solve the enormously difficult problem of separating a faint planet's light from its blindingly bright parent star. It's worth pausing, too, on just how much groundwork had to be laid before this single, faint orange point of light could even be confidently identified. Webb had already spent roughly 3 years in operation, since it began returning science images in mid-2022, steadily refining and calibrating its coronagraphic instruments across dozens of other observation programs before this particular team turned its attention specifically to TWA-7. The star itself had already been studied for years by ground-based telescopes precisely because of its unusually convenient face-on viewing angle, which had already hinted indirectly that something might be hiding in that gap in its disk long before Webb's coronagraph ever confirmed it. This wasn't a lucky, unplanned accident. It was the product of a carefully targeted observation, aimed at a specific star system chosen because prior research had already flagged it as an unusually promising candidate, executed using an instrument built and calibrated over years, specifically to solve the enormously difficult problem of separating a faint planet's light from its blindingly bright parent star. So here's the honest, complete picture, and it needs no exaggeration to be worth genuine excitement. James Webb captured its first direct discovery of a brand new exoplanet, a Saturn-mass world called TWA-7b, orbiting a young star 111 light-years away, sitting in a gap it likely carved into a surrounding ring of debris. It's the lightest planet ever directly photographed around another star, roughly 10 times lighter than the previous record holder, made visible only through the careful combination of a precisely engineered coronagraph, painstaking image processing, and computer simulations built to confirm that what the telescope saw truly matched what a real planet in that exact location should look like. The team publishing the result was candid about the small remaining chance of error, and transparent about exactly how they ruled out the alternative explanation of a background galaxy. And the scientists involved, from the lead researcher to outside experts reviewing the work, describe its real significance not as a single isolated headline, but as the opening of an entirely new category of exoplanets that Webb, and whatever comes after it, can now begin to explore in detail for the very first time. That's the real story behind a headline that, for once, doesn't need a single invented detail to earn genuine astonishment. A 3-year wait, a carefully chosen target star, a faint orange point of light hiding inside a ring of cosmic dust, and a peer-reviewed confirmation that humanity's most powerful space telescope had finally, directly, with its own eyes, found a world we didn't already know was there. If that doesn't feel remarkable enough on its own, it's worth remembering that every other planet ever found this way had to be at least 10 times brighter just to be noticed at all. TWA-7b is the quiet, faint beginning of an entirely new chapter in how we search the galaxy for other worlds. And unlike so many of the headlines circulating about deep space right now, this one is simply, verifiably, wonderfully true. There's something worth sitting with, too, in just how understated the actual announcement of this discovery was compared to the magnitude of what it represents. There was no dramatic press conference, no countdown, no breathless, any minute now, anticipation building. For weeks beforehand, the way there so often is with more speculative space stories, A team of researchers quietly published a paper in a scientific journal describing a faint point of infrared light, a careful statistical case for what it most likely was, and an honest accounting of the small chance they might be wrong. That's what a genuine, historic first actually looks like in practice. Not a dramatic reveal engineered for maximum attention, but a careful, patient, peer-reviewed conclusion, built up piece by piece from real data, real modeling, and real scientific caution. In an information landscape increasingly crowded with manufactured urgency and invented confirmations about far more sensational-sounding claims, it's worth remembering that the real breakthroughs in space science usually look exactly like this one did. Quiet, technical, thoroughly checked, and, if you take the time to actually understand what happened, genuinely awe-inspiring all on their own.